To perform measurements in the infrared, that is to say from 1000 to 3000 nanometers, we need to change a few aspects of the IDR300. We need a different detector, the lead sulfide detector in lieu of the InGaAs detector. We need a different input optic, and we need AC detection electronics instead of the detection electronics housed within the IDR300. Infrared is heat. The signal from the source may be confused with that of heat emitted from the background, the structure of the monochromator, etc. It is for this reason that we, in infrared, must optically chop the signal. Optically chopping the signal is effectively modifying the signal on a known carrier wave and effectively seeking that signal in the detection electronics and ignoring any DC base level. The optical chopper provided is the 218 optical chopper, and a set of blades has been provided. And here we will use a 10-slot blade. For the first time, we need to set up the infrared input optic. It consists of a calcium fluoride based relay optic. We have a mount for the optical chopper which will sit on the relay optic, and we will also discuss the use of the sphere, the D8 sphere, as an input optic. The 10-slot blade should be positioned on the shaft of the 218 optical chopper, and the 3 retaining screws attached to hold the blade in place. We will then proceed, having firmly secured this, to attach this entire mount to the calcium fluoride based input optic. The calcium fluoride lens system is used for the reason that calcium fluoride transmits throughout the region, as opposed to, for example, glass or quartz. So we've fitted the blade, and the optical chopper is driven by a DC motor with power provided from the 218 module, the optical chopper controller. To the base of the optical chopper is an IR emitter receiver, so that as the blade turns, the IR emitter receiver output varies accordingly, and that is returned to the detection electronics as a reference. So that is the known frequency of chopping the source under test. We then remove the clamp of this assembly and then place thereupon the relay optic. The groove of the relay optic fits over the chopper blade, and one can place the clamp in place, attach it more or less, not entirely, before ensuring that the blade moves freely, adjusting position as required, and then finally tightening the clamp up. Once you have done this, you can simply keep this relay optic in this way, paying attention not to hit the blade, else it will be bent. We can remove directly the fiber bundle adapter plate from the entrance slit of the monochromator and fit the infrared relay optic to the entrance port. I only use the top 2 screws for ease of access, and the orientation should be such that the optical chopper is closest to the monochromator, so we must make sure that this is the case. And I will attach that firmly, and we have that as input optic. Now, the calcium fluoride input optic is in a sense intended for use with the D8 integrating sphere. So the D8 integrating sphere can be used for the measurement of absolute irradiance. In practice, I recommend not to use this item. The reason being that in the infrared, sources emit very little light, detectors are not very efficient. The use of an integrating sphere, or like a diffuser, results in a very great loss in the signal through to the monochromator. Effectively, the light input through the port of the integrating sphere is effectively spread across the area and a very small amount coupled to the monochromator. So we can expect a reduction in signal of perhaps 1/100th. So I would certainly recommend avoiding the use, although it can be used with the FOP UV for some measurements above 1100 nanometers, paying attention of the 1380 quartz absorption. And one can also purchase a glass fibre bundle for extending the measurements, certainly up to the range of InGaAs 1700 nanometers. This D8 has also an adapter ring which will attach to the front face of the CL6 for the purposes of calibration. We need now change the detector, the InGaAs detector for the lead sulfide detector, and we need also set up the detection electronics. I will turn round the IDR 300 so we can get a better view of the changes that need to be effected, and then we can start performing measurements. Now I've turned round the IDR 300, we can simply disconnect the signal cable from the InGaAs photodiode and remove the said photodiode from the exit of the first monochromator. Notice that an O-ring used to prevent light leaks has fallen out. We should make sure that that stays in place. I will fit the lead sulfide detector then to the exit slit of the first monochromator. The lead sulfide detector has 3 connections. Firstly, we have one labelled HV for the high voltage to be derived from the high voltage supply in the IDR 300. So where I have switched off the monochromator for the purposes of turning round. Where it's switched on, you should switch off the high voltage using the switch and move the high voltage across from the PMT to the lead sulfide detector. The signal port of the detector should couple from the detector over to input 1 of the 477 amplifier, which is here to the far left of the 417 detection electronics unit. We have 2 similar 5-pin cables. We must not clearly confuse the 2 connections. The first is a 5-pin connection from the 218 module, the optical chopper controller, and that should be connected to the optical chopper. The second connects the CPS1 detector cooler unit to the rear port of the detector for the purposes of cooling. Cooling infrared detectors improves their performance. This detector has a Peltier-based cooling system. Note that these 5-pin connectors have a specific orientation and a collar locks the connector in place. Now we have set up the system. I will turn the IDR 300 round in its manner in which we normally use it, and we will look at the calibration measurement. Before we proceed to calibrate and measure, I will say a few words about the detection electronics. As we've said, the 218 module drives the optical chopper and the reference signal is returned to the 218. This reference is output from the 218 to the 496 DSP lock-and-eye amplifier. The optically chopped signal goes through the monochromator, is detected, and the signal returns to the 477 transimpedance amplifier. This provides gain to the signal, the output of which goes into the lock-in amplifier. In essence, the lock-in amplifier compares the input from the amplifier and detector with that of the reference to effectively extract the signal to be measured. The detector is cooled using the CPS-1M module. This is set to half an amp in factory, which will obtain around -10 degrees device temperature. I've powered on the mains of the 417, and we can connect the USB and power on the unit. The 496 lock-in amplifier will boot, and with the CPS-1M toggle to on position, it will gradually settle at 0.5 of an amp. This will vary with the ambient temperature in the room. We have fitted a 10-slot blade, so the dial on the 218 optical chopper, which sets the frequency, reads correct, as opposed to the use of other blades in the set provided. We tend to recommend measurements at 175 or 225 Hz, but certainly not a multiple of the mains frequency. So if I set the optical chopper to 175 Hz and lock the dial in place using the retaining tab underneath. Now we can set up the system to calibrate. We are measuring effectively, in this case, a relative spectrum in the infrared using the CL6 as the calibrant, which has been provided with a calibration up to 3000 nanometers. We need only position the CL6 at 200 millimeters from the front face of the relay optic. The distance is essentially not important, it's just some point of reference. This is a relative measurement. The more light we measure, the better, but clearly we cannot go too close to the relay optic, much like the spectral check measurement. So we can ensure the 605 is set to 6.3 amps, and we can power the source on, and then we can go and initialize Bemin Plus in the infrared configuration and perform the calibration. So I have set the CL6 to 200 millimeters from the source, and I've merely aligned it such that the emission of the CL6 is concentric with the input to the relay optic. You can now go to Bemin Plus and initialize in the infrared configuration, ensuring of course that the 417 and IDR300 are powered on and connected to the computer via USB. This measurement is perhaps difficult to set up, but easy to perform. And we will see we can simply go, when the system has initialized, to the scan setup page to directly perform a measurement of the source and the calibration source to calibrate the system. Now the system is nearly finished, and we can go to scan setup. We have custom wavelength files merely in keeping with the remainder of the system. Infrared is stepping from 1000 to 3000 nanometers in 10 nanometer steps. And let's effect 5 scans for the moment with no data correction. And we will let that do the 0 calibration and the 5 scans. We will pick that up again in a short time. We have now finished the calibration measurement with the CL6, and I have powered off the 605 power supply. We can, in the same manner as before, take the average of the measurements taken out with the warm-up period of the lamp to apply data correction. I will just save here in the first instance the raw data. It's always useful to have the raw data. I will simply take the average of all in this case and delete the original spectra to give me merely the average, which I will save as IRCL6 average. And we can proceed to go to data correction. The certificate file is the file, the CL6 file, which is named extended, and this, once selected, will always be selected. The system file is the average we just saved. We calculate calibration data and apply data correction, and for reference we return to the calibration folder to save the calibration for future reference. Now if we go to scan setup, data correction is indeed selected, and we will now proceed to measure another source, a incandescent source, in this case for the MR16 that we've considered. In all other cases emits no light in the IR. Now we will perform a measurement of a halogen spotlight GU10 source. This is a source with merely an aluminium reflector, so unfortunately we won't see any nice interesting spectra like you do with dichroic reflector based sources. We set up approximately 200 millimeters from the source to the front face of the Rayleigh optic. Again, this is a relative measurement, so there's no real importance in having any particular measurement distance. And the measurement we will perform here will, when you do this measurement correctly, be attached, as we've said, to measurements of an irradiance of the source between 200 and 1100 nanometers, or certainly up to 1100 nanometers, which we've not looked at in this series of videos. So we will power the source on. We can make some approximate alignment through the alignment utility, and we can proceed to measure the source in the infrared. In order to obtain a maximum of signal, it is quite convenient to use the alignment utility at a suitable wavelength in the infrared, such as 1000 nanometers, to optimize the lateral and vertical positions of the source to be measured, and we can just perform some very approximate adjustment to see how well or not we are aligned. And in this case I need not have changed it much. So I will close, and I will now perform a measurement with data correction applied. I will perform one single scan. Hitting new scan, we see that the y-axis has risen signal in arbitrary units in the same manner that we have done so in the spectral check configuration. And this is merely to avoid confusion between this measurement and an absolute measurement. This is not an absolute measurement of irradiance of the source. This is merely a relative spectral measurement. And we will look at the result when it is finished in a moment. We now have the measurement result showing a fairly typical response for this type of lamp. The relative shape of the source in the infrared showing some features perhaps due to the transmission of the glass front face of the source and attenuation in the long wavelength region. This is quite a different story from, for example, a dichroic source, filter-based source, where you see swooping interference fringes throughout the scan range. We would, in the PSL Wizard, incorporate this scan with an absolute irradiance measurement of the source to perform analysis over the full range, 200 to 3000 nanometers. We will save this as the infrared of halogen spotlight, and that concludes the measurements here. Having finished the measurements in the infrared, we can return the IDR300 back to its most common state, the DC configuration. We can remove the relay optic and fit the fibre bundle adapter, remove the lead sulfide detector and fit the InGas detector, and return the high voltage supply to the photomultiplier and remove the 417, which we will not need. In a nutshell, those are the measurements to IEC and EN 62471, incorporating also the requirements of IEC TR 62778. In the series of videos, we will add some presentations to go through the measurements and measurement techniques to guide you in the use of the IDR300 PSL system in the evaluation of photobiological safety.